Well, my dear students, let me continue the second session. A very interesting topic, that is irreducible polynomial. Polynomial which we can't reduce it. That means we can't split it. Splitting means what? You know, x square plus 2x plus 1 can be written as x square plus 1 into x square plus 1. That means polynomial of higher degree into the lower form. X square plus 2x plus 1 is a polynomial of degree 2. If I split it, how we write x plus 1 into x plus 1 into x plus 1. First polynomial x plus 1, I mean the linear polynomial, is of degree 1. The another one, same, x square plus x plus 1 is also of degree 1. X square plus 2x plus 1 can be written as x plus 1 into x plus 1. This is a polynomial of degree 2. Let me split this polynomial into a lower form. First polynomial, second polynomial. Both are linear, that means degree 1. So we call this one as reducible. Now we have to study irreducible polynomial. The definition is like this. A non-zero polynomial p of x in the set of polynomial rings. Set of polynomial rings means it will satisfy all the laws of rings. Okay, is said to be irreducible if you are able to write p of x as a of x into b of x. The condition is what? Either a of x or b of x is of degree 0. Is possible only when it is a constant polynomial. Constant polynomial means x to the power 0 or unit. For example, if we have 1, then we write it as x to the power 0. Okay. Now we'll take examples. X square plus 1 is a polynomial. This is a polynomial of degree 2. This is a quadratic. Quadratic means degree 2. Is irreducible over R. Over R means if it is a set of real numbers, we can't write it, we can't split this one into the polynomial of lower degree. But it is reducible over set of complex numbers. That means in place of R, in place of real number, if we take complex number, in place of R, if we take complex numbers, then we write x square plus 1 as x plus I into x minus I complex number. That means we can rewrite this polynomial into x plus I into x minus I only when the field is complex. If it is real, I'm sorry, that means it is not reducible. That means irreducible. If it is a real set of real numbers, if it is a set of rational numbers, if it is a set of integers, then it is irreducible. Let me take another example. X square minus 2. Again, it is a quadratic polynomial. We write x square minus 2 as x plus root 2 into x minus root 2. Here we rewritten x square minus 2 as x plus root 2 into x minus 2. Root 2 is what? Is irrational. That means set of real numbers. Therefore, this polynomial is reducible over real numbers but not on set of integers, because here we can't replace x by set of any integer. Therefore, x square plus 1 is reducible over complex number, but it is irreducible over R, set of real numbers. If I take second example, that is x square minus 2, it is reducible over real numbers. Real number may be rational or irrational, but it is irreducible over Z. What these two examples shows that the polynomial may be reducible or irreducible. It all depends on what field. Okay, if you choose correct, if you select the correct field, then it is reducible. Otherwise, it is not reducible. Let me take an example. Show that x square, not x square, x cube minus 9 is reducible over integer modulo 11. Okay, using synthetic division method, you know the synthetic division method. Let me repeat, using synthetic division method, we write x cube minus 9 as x minus 4 into x square plus 4x plus 5 over integer modulo 11. The polynomial certainly reducible. If I replace x by 4, what we get? 0. That means this is a polynomial of degree 3. We split this polynomial as x square minus 4. That means linear polynomial into what? Quadratic polynomial. That means polynomial of higher degree into the lower form. This is first polynomial of degree 1, that is linear polynomial, and this is a polynomial of degree 2, that means quadratic polynomial. Now I will take an example which is irreducible over integer modulo 3. Integer modulo 3 means it has only 3 elements. The set has 3 elements, 0, 1, 2. If I replace x by 0, it is not equal to 0. Not equal to 0 means we can't split this polynomial into the lower form. If I replace x by 1, again not equal to 0. That means we can't split the polynomial of higher into lower form. Similarly, if I take x equal to 2, again it is not equal to 0. Not equal to 0, whenever we get not equal to 0, that indicates it is irreducible. The reducible means it should be equal to 0. Okay. Let me take another example. Show that x square plus x plus 4 is irreducible over integer modulo 11. Follow follow the same procedure. Definitely, if x equal to 0, x equal to 1, x equal to 2, x equal to 3, for all the values from 0 to 10, it is irreducible. That means it is not equal to 0. Now, the interesting polynomial, that is primitive polynomial. A polynomial is said to be primitive if the GCD of the coefficients, that is a0, a1, a2, an equal to 1. If the GCD of the coefficients of the polynomial is 1, that means if they are relatively prime, then the polynomial is said to be primitive polynomial. That if the GCD is 1, that means they are relatively prime. Okay. Let me take an example. The constant term 1, coefficient of x square is 5, coefficient of x cube is 8. All these constants 1, 5, 8 are divisible by only 1. That means GCD is 1. The GCD is 1. Remember, the GCD is 1. Then the polynomial is said to be primitive. Okay. Now, one important lemma. We call this lemma as a Gauss lemma. The statement is like this. If the primitive polynomial means the GCD of the coefficients is 1. If the primitive polynomial, that is f of x, can be factored as the product of two polynomials having rational coefficients, it can be factored as the product of two polynomials having integer coefficients. That means if the polynomial is primitive, then it can be factored as a product of two polynomials having rational coefficients. The coefficients are rational, and again there are coefficients will take the integers. Okay, let f of x, let me take a polynomial, and we denoted that polynomial by f of x. F of x equal to g of x dot f of x dot f of x equal to g of x dot h of x. Since g of x and h of x are both polynomials, when we have a polynomial, definitely certainly we will see the constants. Let me denote the constants by the notation a by b. The constants of g of x and h of x, I will denote it by a by b. Rewriting, the constants are integers, both that is lambda x. When we rewrite g of x into h of x, we get a by b into lambda of x into mu of x. Both lambda of x and mu of x are having integer coefficients and they are primitive. Primitive means the GCD of the coefficients is 1. When you cross multiply, what do you get? If you cross multiply, we get b dot f of x is equal to a into lambda of x into mu of x. Since left hand side is primitive, that means the GCD of the coefficients is 1. Therefore, the left hand side is also what? Primitive. Here, the numerator may equal to denominator. Possibilities I am writing. Or if you divide the numerator by denominator, that means a by b is 1. At this, if these two, if a equal to b or a by b is 1, then f of x is equal to lambda of x into what? Mu of x. This completes the proof of the Gauss lemma. This lemma will help us to prove an important theorem, that I will take later. Product of two primitive polynomials. Let me take an important result. The product of two primitive polynomials. I'll denote the first polynomial by f of x and the second polynomial by g of x. Okay, the coefficient of x to the power m is a to the power m. It is not equal to 0. That means the degree of this polynomial is m, because the coefficient is not equal to 0, and the degree of second polynomial is n, because its coefficient, that is bn, not equal to 0. Both are primitive. Both are primitive means the GCD of a0, a1, a2, am is 1. GCD of b0, b1, b2 and bm is also 1. That means both are primitive. Let me multiply these two polynomials. If I multiply these two polynomials, we get a polynomial which is of this type. C0, that means the product of these two polynomials is of the form C0 plus C1x plus C2x square and so on. Generally, I denote this Ci. I mean the product of, when we multiply these two polynomials, we get a polynomial which is of this nature, where Ci is ai b0 plus ai minus 1 b1, ai minus 2 b2 and so on up to what? a0 bi. You see, ai b0, at the end what do you get? a0 bi. Initially ai, here bi, b0, here a0. And we know that the GCD, since the GCD of the coefficients is 1, therefore the GCD of C0, C1 is also, let me take this one as D. We have to show that D is 1. we have to show D is unit, that means 1. Let me prove this theorem by contradiction method. If possible, D is a non-unit. Actually, we should get unit, that means 1 here. If it is non-unit, what will happen? If it is a non-unit, there exists a prime element. Prime element means, it may be 2 or 3 or 5 and so on. There exists a prime element such that P divides D. P divides D. Since both are primitive, we know that both are primitive, that the GCD of its coefficients, the GCD of your coefficients is 1. Very interesting point. Listen to my words carefully. We have so many coefficients in f of x as well as in g of x. Let aj be the first coefficient of f of x which p does not divide. Actually, what we have here, p divides d. Let aj be the first coefficient of f of x which p does not divide. Similarly, bk be the first coefficient of g of x which p does not divide. That means all the coefficients we can divide, all the coefficients will divide by p, but only aj in f of x, bk in g of x will not divide. The coefficient, if you multiply these two polynomials f of x and g of x, the coefficient of x to the power j plus k, aj from f of x, bk from g of x. The coefficient of x to the power j plus k is cj plus k. When you multiply, certainly we get a coefficient. We denote that coefficient by cj plus k, where the product of two polynomials, that is f of x into g of x. When you multiply these two polynomials, we get a term like this, cj plus k. Cj plus k will have the terms of this type, aj bk, j plus 1, j plus 2, j plus k, go on increasing a terms, that is suffix of a, and decreasing the suffix of b. Here k, k minus 1, k minus 2, up to what? b naught. If you multiply these two polynomials, we get a terms of this nature. Go on decreasing the suffix of a. Here we have j plus 1 up to j plus k. After that, go on diminishing, j minus 1, j minus 2. Okay. At the same time, k minus 1, here we have k plus 1, k minus 2, here we have k plus 2, and so on up to what? bj plus k. Let me introduce the bracket. This is one term. The entire bracket is second term, and the last one from here to here. What is our choice? Our choice of aj and bk. By our choice of aj, p will divide aj minus 1, p will divide aj minus 2, and so on. But p will not divide. Remember, p will not divide aj. Other than aj, p will divide. P had a friendship with all the elements, all the coefficients of f of x except aj. For aj is the enemy of what? Here p. Here bk is the enemy of what? P here. I mean in AJ is the coefficient of f of x. P does not like this. Bk is the coefficient of g of x, which P does not like. That means other than these two elements, P will divide that. Here we can see P divides Aj minus 1, not Aj. P will divide Aj minus 2, not Aj, and so on. That means P will divide this bracket. I mean the second bracket, because here we have Aj minus 1, Aj minus 2. Therefore, I am forced to take the second bracket. Similarly, of the choice of Bk, Bk is the coefficient of g of x, which P does not divide. That means other than Bk, all the elements, P will divide all the elements. That is Bk minus 1, Bk minus 2, and so on. So that means I have to take the first bracket, that is this one. P will divide Aj plus 1, Bk minus 1, and so on. But our assumption, what is our assumption? Our assumption is like this. P will divide D. P will divide D. What is D? D means the coefficient of x to the power j plus k is Cj plus k. Thus, P divides Aj minus Bk is not possible because Aj be the first coefficient of f of x, which P does not divide. Bk is the first coefficient of g of x, which P does not divide. Okay, what it shows? This shows that P does not divide Aj minus Bk. That means P divides Aj minus Bk is highly impossible. That because P does not divides Aj, P does not divides Bk, which is a contradiction. Hence, the product of two polynomials must be primitive. Primitive means the GCD of the coefficients of both the polynomials, that is f of x and g of x, is what? 1. That means this is possible only when D is what? Unit. This completes the proof of the lemma. Now, one more important result that is very interesting. Eisenstein's criterion. The statement of the theorem is like this. A polynomial f of x with integer coefficients. Suppose that for some prime integer, let me take that prime integer p. Whenever we see a polynomial, definitely the coefficients will be there. P will divide the first coefficient of f of x, that is constant term. P will divide the coefficient of x, that is a1, and so on. P will divide, listen to my words carefully, P will divide what? X to the power n minus 1 coefficient, that is an minus 1. But P will not divide the coefficient of x to the power n, that is an. P divides a0, P divides a1, P divides an minus 1, but not P divides an. Let me recall the previous theorem. Aj be the first coefficient of f of x, which P does not divide. Similarly, Bk is the first coefficient of g of x, which P does not divide. Similarly, in the Eisenstein criterion, P divides all the coefficients of f of x except an. Since P does not divide an, that means the coefficient of x to the power n, and p square means the square of the prime integer. P square does not divide an also. Since p does not divide an, therefore p square does not divide an. This is possible only when the polynomial is irreducible over what? Over the field of rational. That means f is set of rational numbers. So very important theorem and interesting also. The proof is very simple. You can understand this theorem only when you understand the previous one, that is product of two primitive polynomials. Okay, let me take a polynomial and we will denote this polynomial by f of x. A naught constant term, coefficient of x is a1 and coefficient of x to the power n is an. P does not divide an, but it will divide a naught, a1, a2 up to what? An minus 1. Very interesting. P has a friendship with this, this and this, but not with this. Since it is not made any friendship with this an, therefore p square is not divisible, it does not divides what? An. Let me prove this theorem. Without loss of generality, that means without affecting the result, the result remains same. Without loss of generality, let me take a primitive. Let us assume that f of x is a primitive polynomial. Whenever I use the word primitive polynomial, that means the GCD of the coefficient is what? 1. Okay. By definition of primitive polynomial, GCD of a0, a1, a2 and so on an is 1. Let me split this polynomial f of x. Let me split this polynomial f of x into the product of two polynomials. First polynomial is g of x and the second polynomial is h of x. If since f of x is a polynomial of degree n, certainly the g of x and h of x are the polynomials of degree less than what? N, where g of x and h of x have the rational coefficients. Using Gauss lemma, I'll make use of Gauss lemma here. Initially we have the rational coefficients, then what? Integer coefficients. By Gauss lemma, Gauss is here, it can be factored as a product of two polynomials, that is g of x and h of x, having what? Integer coefficients. When you use, that means initially, listen to my words carefully, initially g of x and h of x are both polynomials of rational coefficients. When we make use of the Gauss lemma, these rational coefficients can be converted into what? Integer coefficients using the Gauss lemma. Let us assume that actually what we want? We want irreducible polynomial. Let me use the contradiction method. Let us assume means contradiction method. F of x is reducible. Reducible means what we get? We get an answer which is equal to what? 0. We have solved examples. Not equal to 0 means irreducible. Is reducible. Let f of x can be rewritten as, this bracket stands for g of x and another bracket stands for h of x. Both, the polynomial, the coefficients of the polynomial b0, b1, br and c0, c1, cs are what? Integers. We are making use of what? Gauss lemma here. If we multiply constant with constant, I denote it by a0. Again, if you multiply the coefficient of x, constant term is b0, c0, I will denote it by a0. If you multiply these two polynomials, what I do now? Now I will take the coefficients of x. The coefficients of x is of the form b1 c0 plus c1 b0, and I'll denote it by a1. Similarly, if you may take the coefficients of x square. In general, if you take the coefficients of x to the power k, we get bk c0, bk minus 1 c1, and so on b0, go on diminishing the suffix of b's and increasing the suffix of what c's, and I'll denote it by what ak. Let me take the constant term, that is a0. Since P divides A0, according to the statement, P divides A0. P divides A0 means P divides B0 C0. Since P is a prime number, using the theory of number results, P divides either B0 or C0. Again, by statement, P square does not divides A0 because P divides a0, but p square does not divides a0. That means p square does not divides b0 c0. That indicates p square does not divides b0 or p square does not divides c0. Let me take p divides b0. If I take p divides b0, that means p does not divide. I should get what? I should get p does not divides c0. Listen to my words carefully. P cannot divide. This word is very, very important. I said earlier also. P cannot divide all the coefficients. It will divide only few elements, or it will not divide at least one element of a polynomial. Let me repeat. P will divide all the coefficients except 1 or 2. P will divide B0, P will divide B1, P will divide BR, except P will not divide AN. That is the last term that you know. To understand this theorem, to complete the proof of this theorem, let me take a small integer. See that P does not divides Bk. What is the condition for R? Let Bk be the first element of B, which P is not divisible by P. Very interesting. Let me repeat. P will divide all the coefficients of a polynomial except one, that is An. To complete the proof of the theorem, I need a smallest integer. Let me take a smallest integer. K be the smallest integer. I'll impose one condition, that is P does not divides Bk. Here R lies between K and N. Bk be the first element of the polynomial, the first, that is g of x. Bk be the first element of P. That means we have B0, B1, B2, B3 and so on. Out of that, Bk be the first element of P which P does not divide, which is not divisible by P. Let me repeat. Bk be the first element of P. That means we have so many elements, B0, B1, B2, B3 and so on. Out of that, Bk be the first element which is not divisible by P. P. That means P divides B naught. This is in words. Let me, if I put in mathematical form, P divides B naught, P divides B1, P divides BK minus 1, except P does not divides BK. Since P does not divides BK means the higher terms also the same. That means P does not divides BK plus 1, P does not divides BK plus 2 and so on. Let me take the coefficient of x to the power k, that is a to the power k, and a to the power, that is ak. The coefficient of x to the power k is this, and we denoted the sum of all the terms as ak. I'll rewrite this statement in this form. I want only the bk term, this term. I am interested in bk term. Since the C0 is with BK, therefore let me take BK C0 one side. On the other hand, remaining terms. Since P divides AK, fine. P divides BK minus 1. P divides BK minus 2, because the condition is what? K is less than N. That indicates what? P divides all the terms except BK. That means sum of all the terms. What it indicates? It indicates P divides BK C0. That means P divides BK or P divides C0 by standard theorem. I mean number theory theorem. But according to our wish, our assumption, P does not divides BK, P does not divides C0, which is contradiction. That means our assumption. What was our assumption? Our assumption was reducible is wrong. Therefore, it should be irreducible over what? The set of rational numbers. This completes the proof of the beautiful theorem. I hope you got it. Practice it. If you have any doubt, call me. Take care of your health. Okay, study well. Have a nice evening. Thank you.